Hello everyone, a very good evening to all. I welcome you all again to this second introduction session on solid state physics course, which is being flowed this July 2024 session by NPTEL with course code NOC 24 PH 43. Myself, Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So, uh, in today's interaction session, I'll be solving a few sample problems that are based on the week 2 lectures mainly, which covers some basic introduction to the crystal structures, types of crystals, 3D, three-dimensional crystal structures mainly, and Miller indices like the direction cosines and direction indices of the planes that are present in a crystal. So, before discussing a few problems, I'd like to give a brief explanation of the crystal structure and other things. So if you talk about 2D crystal systems, as you can see, there are five type of crystal structures in two-dimensional crystal system. The first one is oblique lattice. Oblique. In case of oblique lattice, A is not equal to B. As you can see, this is not equal to this. So, and also the angle between A and B, like the angle which is defined by gamma, that is the angle between A and B, and that angle is arbitrary. That can be any value. So this is called as oblique lattice. And in case of square lattice, as you all know, A is equals to B and the angle is 90 degree. And in case of rectangular lattice, A is not equal to B and the angle between A and B is 90 degree. Again, there is another type of lattice which is called as hexagonal lattice. And in case of hexagonal lattice, if you see hexagonal lattice, the unit cell of hexagonal lattice is nothing but the rhombus. And for rhombus, A is equals to B, and the angle between A and B is 120 degree, as we all know. So this is A, B, and both are equal. And this is the angle. It is 120 degree. So this is rhombus, which is unit cell of hexagonal lattice. And then rhombic lattice, for which A is equals to B and uh, gamma is arbitrary. Centered rectangular lattice. So this is the example of a centered rectangular lattice. So these are the these are a, these are the 2D crystal systems. And talking about the 3D crystal systems, we have 7 crystal structures, and corresponding to 7 crystal structures, we have 14 Bravais lattice. What are Bravais lattice? There are some different types of structures. Like if you consider about a cubic structure, then they can be primitive, they can be body-centered cubic, they can be face-centered cubic, and for other structures, they also can be end-centered cubic. So they also can be end-centered. So corresponding to each type, we have different Brevis lattice. So there are, in case of three-dimensional crystal structure, there is 7 crystal classes and 14 Bravais lattice. So they are cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, and trigonal. So in case of cubic, as you all know, all the primitive vectors like A and B, A, B, and C are called as primitive vectors or unit cell. So in case of cubic, A is equals to B and is equals to C, and also the angle alpha, beta, and gamma all are 90 degree. And in case of cubic, as you all see, P stands for primitive. Primitive means primitive cell are those cells for which the effective number of atom is 1. So only the atoms are present at the corners and they are not present at the walls or inside the crystal structure. So in case of primitive, as there are 8 atoms and 8 corners, so each atom is shared by 8 crystals. So it will be 8 into 1 by 8 is equal to 1. So the total number of atoms in a unit cell is 1. So this is called a primitive. Then body centered, face centered, and side centered or end centered. So in case of cubic, this is primitive, body centered, and face centered. In case of tetragonal, they are only primitive and body centered. In case of orthorhombic, we have all four types of Bravais lattice: primitive, body centered, face centered, as well as side centered or end centered. In case of hexagonal, we have only primitive. In case of monoclinic, we have primitive as well as side centered. And in case of trigenic, we have primitive, and in case of trigonal, we have also only primitive units. So if you see different parameters, these are also mentioned here. There are conditions like whether A will be equal to B or will be not equal to C. And there are some other relationships also regarding alpha, beta, and gamma. And talking about Miller indices. So basically, Miller indices are nothing but the reciprocal of the intercept that a plane forms at the coordinate axis. So if you talk about Miller indices are defined for a set of parallel planes, and Miller indices are the reciprocals of the intercepts made by the plane on the crystallographic axis when they are reduced to smaller number or the smallest number. So if you talk about these examples, so how you will calculate? Suppose this is x, this is y, this is z. Then we will write x intercept, y intercept, z intercept, and the unit vectors a vector, b vector, and c vector along those axes, and we will take the ratio, and then we will take the inverse of it. As I mentioned, it is the reciprocals of intercepts. So it will be a by a intercept. So we can write x by x intercept, y by y intercept, and z by z intercept, and they are called as HKL. They are written in this bracket. So these are the form of Miller indices. And there are a few examples, like if you see, suppose this is x-axis, this is y-axis, and this is z-axis, where the angle between x and y is 90 degree, and the angle between x and z is 90 degree, and also between z and y is 90 degree. So if you see this particular type of picture, in this case, this is parallel to x-axis and y-axis. So this plane is parallel to x-axis and y-axis. So if you see, if you extend this, so this is the plane that is displayed in this figure, and its intercept z is 1. So if you talk about the value of x-intercept, y-intercept, and z-intercept, so for this A, the x-intercept is infinity because it is parallel to x-axis, and again y-intercept is also infinity, and z is 1. So if you do the same thing, we will suppose A, B, C are the unit vectors along x, y, z. So we will write A by infinity, B by infinity, and C by C, because 1 means C. So it will be 1 by infinity 0, 0, and 1. So the Miller indices will be 1. Since it is already the smallest set of numbers, so we can reduce it further. So it is 0, 0, 1. Similarly, in case of this is parallel to, so if you do, this is parallel to Z. So this plane is nothing but in the ZY plane. So for ZY plane, Z and Y intercepts are infinity. So the Miller indices will be 1, 0, 0. Similarly, for XZ plane, Miller indices will be 0, 1, 0. And if you talk about the fourth one, if you see, in this case, this is, if you see, this is uh, parallel to y-axis. So y-intercept will be infinity, and it is cutting the x-axis and z-axis. So it will be 1, 0, 1. Similarly, all these planes can be evaluated, and we in the upcoming in this session we will be solving a few problems that will also cover this type of planes and how to calculate the Miller indices. So some basic ideas how to calculate the Miller indices I just explained to you. And now let's solve a few problems which will be based on the course content of the week 2 of solid state physics course. Now question 1 says projection of a vector OA vector onto the x, y, and z axis are respectively 2a, b, and 2c as shown in figure below, where a, b, and c are the unit cell parameters. Determine the crystallographic direction of the corresponding projection vector OA using the following procedure. What procedure will follow? A vector of convenient length is to be positioned such that it passes through the origin of the coordinate system. Any vector may be translated throughout the crystal lattice without alternation if parallelism is maintained. Measure the length of the vector projection on each of the three axes in terms of the unit cell dimensions A, B, and C. Say UA is the length of the projection on x-axis. Similarly, VB with the length of the projection on y-axis, and WC on the z-axis. These three numbers U, V, and W are then multiplied or divided by a common factor to reduce them to the smallest integer values, say U prime, V prime, and W prime. And then these three integers, not separated by any commas, they are enclosed in a square bracket as U prime, V prime, and W prime. This represents the crystallographic direction. So this question is based on determining the crystallographic direction. So you one thing you should keep in mind: crystallographic direction is not Miller indices. Miller indices are different. Crystallographic directions are directions of particular type of planes or particular type of vectors. So if you see, these are the procedures that we need to follow in order to determine the crystallographic direction of the corresponding vector OA. So these are the options: 2 bar, 1, 2. So 2 bar is nothing but minus 2. So 3, 1, 3 bar, 3, 0, 1, 1, 0, minus 2. So these are the four options. I will give you a few minutes to think about this question and then I will solve it. So let's solve this question. So this is the figure. So this is A, this is B, this is C. Let me choose another color. Pencil. So the OA vector, suppose this is the origin is O, then OA vector, uh, the projection of the OA vector onto X, Y, and Z axis are respectively minus 2A, B, and 2C. So minus 2A means this is minus X, this is minus Y, this is minus Z. So the projection is minus 2A means the OA vector, the projection will be, suppose this is A, so the projection of OA vector is here. And then uh, up to Z axis, of Y axis, the projection is B. So this is the projection at Y axis, and the projection at Z axis is C. So the point is minus 2A, B, and 2C, or minus 2, 1, 1. This is the point. So if you see, suppose we will determine three axes X, Y, and Z. So the intercepts are minus 2A, B, and C. So if we divide these intercept by the unit cells, well, B by B, C by C, so it will be minus 2, 1, and 1. These are already reduced, so we don't need to reduce it further. So it will be 2 bar, 1 and 1. It will be included in square bracket. So this is the direction of OA vector. So the vector will be somewhat like this. So its projection is like here, projection like here, and this is the projection. So this is OA vector. So if you talk about the procedures, a vector of convenient length is to be positioned such that it passes through the origin of the coordinate system. Any vector may be translated throughout the crystal lattice without alternation if parallelism is maintained. So what we will do? So for this, we will move minus 2A along x direction. So we will move minus 2A along x direction. So we move from here to here. We move. This is 2A. Then we will move along y direction by 1 unit. So we will move along y direction by 1 unit. So this is B. So this length is B. And then we will move along z direction by 1 unit. So this is C. Sorry, let me. So the question was minus 2A, B, and 2C, not C. So this is 2C. So this will be, if C is here, so this will be the vector. It will be like this. This is 2C. So this is 2C, this is 2, and again this is 2. And the next step, measure the length of the vector projection on each of these three axes in terms of the unit cell dimension. So this is 2A, 2 into unit cell dimension A, 1 into unit cell dimension B, 2 into unit cell dimension C. Then these three numbers U, V, W, these are the three numbers. This is U, this is V, and this is W. Or multiplied or divided by a common factor. So there are no common factors here. So this number will be like as it. Then these three integers not separated by comma. So there will be no commas in between. And when they are enclosed in a square bracket, this is called as crystal. They represent the crystallographic direction. So the correct answer will be -2, 1, 2. So this is the correct option. Option A is the correct. If you see, this is also drawn here. -2A in X direction, B in Y direction, and 2C in Z direction. This is -2A, this is B, and this is 2C. So -2, 1, 2. It will be -2, not minus, sorry. This will be 2 bar 1, 2. So the correct option is option A. I hope this is clear to everyone. Then we move to question number 2. The question number 2 says, choose the correct directional indices corresponding to the vector OP as shown in the figure, which represent the crystallographic direction. The options are option A 110, option B 023, option C 101, and option D -2 1 -1. So this is the picture. So for your clarity, let me draw this picture once again. So this is the picture we have. This is X, this is Y, this is Z. So the picture is OP. This is O, this is P, this is A, this is B, and this is C. And you need to find out the correct directional indices of this vector OP, that is the projection in terms of the unit vectors. So I'll give a few minutes you to try this question and then I will discuss. So let's discuss the second question. So choose the correct directional indices corresponding to the vector OP as shown in the figure. So this is OP. So if you see, the O is the origin of the coordinate system, that is 0, 0, 0, and we need to find the coordinates of the point P. So if you see, the projection of OP along the x-axis is A, and the projection of OP along the z-axis is C. And since it is not passing, so since it is passing through xz plane, so in xz plane, y equals to 0 always. So y will be 0 into b. So if you do the same thing like the previous question, x, y, z projections A, 0, C, then in ratio A by A, 0 by B, C by C, it will be 1, 0, 1. So since they are already reduced to smallest numbers, it will be 1, 0, 1. Direction of OP vector. So the correct option will be 101, that's it, option C. Then question number 3, find the directional indices of the vector OP within the cubic unit cell as shown in the figure below. Consider the lattice parameter of the cubic crystal is A. So here this is a cubic unit cell. So in case of cubic, A equals to B equals to C. So we will write A for X, Y, and Z. So options are option A, minus 1, 1, 1, 1, minus 1, 1, minus 1, minus 1, minus 1, 0, minus 1, minus 1. So these are the four options. And if you see the picture clearly, so the arrow is like this. This is P and this is O. So we need to find the direction of OP vector, means the direction will be like this towards the origin. So you need to find the correct directional indices. So this is an interesting question. So I will give you a few minutes to try this question and then we will discuss. So if we discuss this question, the vector OP. So in order to find the actual direction, we need to place the tail of this vector, that is point P, at the origin O. So if we do the same, then what will happen? Then this point, if you see this point, this point is nothing but 1, 1, 1, 1, 1, 1. So this is the corner. So we have moved one point along Z axis, along Y axis, and along X axis. So if you follow this path, this is A, this is also A, and this is also A. Or you can follow any path. You can follow this. This is A, this is A, and this is A. If you follow any path, you will be displacing one unit along each axis. So you will reach that point P. But since the direction is opposite, so the if you replace the point, so now let's do the figure. So this is X, this is Y, and this is Z. So this is the point from here to here. We need to measure. So this is O, this is P. So now, if we define the origin at the point P, then what will happen? Suppose this is our origin. This will be Y. So this axis will be X. This will be Z. So if you see, this is the starting point of the vector OP. The direction is like this. So if we move one point down, so this will be minus A, one point along minus y axis, because this is minus y axis, this is minus z axis, and this is minus x axis. So one point down along z axis is minus a, one point towards minus y axis, so this is minus a, and then towards minus x axis, this is minus a. So it will be minus a, minus a, minus a. So x, y, and z will be minus a, minus a, and minus a. So if you divide minus a by a, minus a by a, minus a by a, minus 1, minus 1, minus 1. So since these are already reduced, it will be minus 1, minus 1, minus 1 in square bracket. So this will be the detection of this vector OP. But why this is minus, this became minus 1, minus 1, minus 1. So sorry, we don't write it this way. This will be 1 bar, 1 bar, 1 bar. So this is the so which of the following will be the correct option? Option C will be the correct option. Because the direction of the arrow was towards the origin, so in order to find the actual direction, we need to place the starting point of the vector at the origin. In the previous questions, the starting, if you see, so in the previous questions, The starting point was origin here, and then the arrow was away from the origin. That's why we are following the conventional method. But here we will not follow the conventional method. Then question number 4. Determine the indices for direction shown in the following cubic unit cell. So this is again a cubic unit cell. Consider the lattice parameter of the cubic unit cell is A. And the options are -2, 1, 0, -1, 2, 0, 0, -1, -2, -1, -2, -3. So this is also an interesting question. In this case, the arrow is different, and again the direction is also a bit different from the previous questions. Like in the previous question, we shifted the origin. Here we also we will be needing to shifting the origin. I'll give you a few minutes to try this question, and then I will discuss. So if we discuss this question, this is X, this is Y, and this is Z. So if you see the ZY plane, so the in case of ZY plane, like this is sorry, this is Z and this is Y. To see to give you the actual view, this is like this. You should remember I am talking only about the ZY plane in 2D. So the correct answer will be different, but the approach will be like this. So in case of ZY plane, so this point, so this part is A by 2. So and then X along the X axis, it is A along the X, Y, and Z axis. Since it is a cubic unit cell, all the parameters are A. And along Y axis, you can see the intercept is A by 2. So what we will do first, we will position the origin of the coordinate system at the tail of the direction vector as shown in the figure. So what I will do, I will keep the origin here. This is X, this is Y, this is Z. So if you see here, X, Y, and Z, the projection, since the point is, so this is the actual vector. So since the origin is here and is crossing through x equals to 0, so the x projection in terms will be 0. And in case of y, it is my a by 2, it will be minus a by 2 as we have moved the origin. And in case of z also, since we have moved, it will be minus a. Then if you reduce it to integers, it will be 0 by a minus a by 2 minus a by 2a minus a by a. It will be 0 minus 1 by 2 and minus 1. So if you multiply 2, it will be 0 minus 1 minus 2. So the correct option will be 0 minus 1 minus 2. So the correct option will be 0 minus 1 minus 2, option C. Since it was cutting the y-axis at minus a by 2, but the direction goes, but the crystal directions can contain any reciprocal numbers. So you will be multiplying 2 to all these three numbers, which will give us 0, minus 1, and minus 2. So since we moved in negative direction, that's why minus signs arises. So the correct option will be 0, minus 1, minus, that is option C. Then question number 5. Determine the Miller indices of the plane A as shown in the figure below within the unit cell having the unit cell parameter A. Again, this is the cubic unit cell and the parameter is A. And here we need to here we need to find the Miller indices of the plane. So we don't need to find the directions. We need to find the Miller indices, that is the reciprocal of the intercepts that the plane makes at each particular axis. So since we have already discussed these types of planes, so the options are option A 0, 0, 1, option B 0, 1, 1, option C 1, 0, 1, and option D 1, 1, 1. So if you see this plane cuts z axis at A and it is parallel to x axis and y axis because this plane lies in the xy plane. So the dashed plane lies in the xy plane. So this is x direction and this is y direction in this figure. So this plane lies in the xy. This plane lies in the xy plane. So since this is parallel to both x axis and y axis, so if one plane is parallel to one plane is parallel to axis, that plane has an intercept of infinity onto that axis. So if you talk about three axes x, y, and z, and if you talk about the intercepts, then since it is parallel to x axis, x intercept will be infinity. Since it is parallel to y axis, y intercept will be infinity. And since it is cutting the z axis at A, it will be A. Then according to the procedure of Miller indices, we will divide x by x intercept. So x by x intercept, y by y intercept, z by z intercept. It will be x by infinity, y by infinity, a by A, or Z by A. It will be 0, 0, Z also. Also here, the unit cell parameter is A. So it will be 0, 0. This is Z or A. We can say A by A is 1. So it will be 0, 0, 1. So the correct option will be option A, 0, 0, 1. So this 0, 0, 1 is the Miller indices of the plane. So it cuts the Z axis at A and it is parallel to X axis and Y axis. So if you see this plane is parallel to X axis and Y axis and it cuts the Z axis at Z equal to A. I hope this is clear to all of you. Then question number 6. This question is similar to the previous question. We all again need to determine the Miller indices of the plane OPQR. This is the plane OPQR within the unit cell having unit cell lattice parameter A, B, and C respectively. So this is the plane. This plane, like the previous question, it was parallel to X and Y axis, but it is not parallel to any of the axis. So it is passing through the body of the cubic structure. And in case of this particular structure, A, B, and C, these are different. So we will be considering unit cell unit vector along X is A, along B is Y, and along Y is B, and along Z is C. And the options are -1, 1, 0, 1, -2, 0, 3, 2, 0, -2, -1, 0. So I will give you a few minutes you to think this question. Then I will discuss. So if we talk about this particular question, you see, like in the previous question, so when we are determining the direction indices, the crystallographic directions of particular vectors, then we were shifting the origins to the starting point of that vectors. So like here we will do the same thing, but we will what we will do, we will shift the origin so that the origin of the system does not lie at any point within the crystallographic plane that is shown here. So what we will do, suppose we will again draw the picture. So this was the initial origin O. So this is Y, this is X, and this is Z. So the plane was this. In order to move the origin, so what we can do? So if you go on this way, you will not be able to move away from the plane. If you go this way, 1 minute. So if you go this way and reach this point, you will be again inside the plane. And if you go this way, you will be reaching here. You will be again inside the plane. So if you move the origin along the x direction to here, then you will be away from that plane. So suppose we move the origin in this x direction. So the new origin will be, so this is 0. So this point we need to, so this is 0 now. So this will be y, x remains fixed, and this is z. So we moved. So if this is 0, so this point is nothing but minus a. For now, this point is minus a because this is minus x-axis. So this point is minus a, this is z, and this is y. Y is plus a. So this is a. And if you see this plane, so if you see the plane is intersecting two axes, x and y, and it is parallel to z. So the x intercept is -1, minus, minus a, and y intercept is a now, because we shift the origin. So if we do the same thing like the previous question, what we will do, it will be x by x intercept, y by y intercept, z by z intercept. So x is a by x intercept is minus a, y is a by y intercept is a, z is a, and z intercept is infinity. So it will be -1, 1, and 0. So since it is already reduced, so we don't need to reduce it to obtain the Miller indices. So the correct option will be -1, 1, 0. So the correct option will be option A. So I hope this is clear to you. So what we did, we just moved the origin. So see, we move the origin to here. With respect to this origin, this point is minus a because this is the plus x direction. So this is minus a, this is a, and this is parallel to z axis. So it is not intersecting any z axis, but previously it was intersecting the z axis. So since this point is far away from z axis, so this is parallel to the z plane. So the new intercepts will be minus a and infinity. So since this is minus a and infinity, so if you take the reciprocal, it will be -1, 1, and 0. It is a by minus a by a, and a by infinity. So the correct answer will be option A, that is -1, 1, 0. I hope this is clear to all of you. Then question number 7, the space lattices with two lattice parameters belong to the crystal system. So the options are option A, tetragonal, rhombohedral, hexagonal, option B, triclinic, option C, monoclinic, and option D, cubic. So if you go to the initial slides, today we discussed the three-dimensional crystal structures. Now, if you see here, in case of cubic, A is equals to B is equals to C. So we can assume that A as the independent parameter. Since A, B, C are equal, so there is only one unit vector here. So in case of cubic, since all parameters are equal, so there is only one lattice parameter, that is A. But in case of tetragonal, since A equals to B not equal to C, so there are two lattice parameters. In case of orthorhombic, there are A not equal to B not equal to C, so there are three lattice parameters. In case of hexagonal, A equal to B not equal to C, so there are two lattice parameters. In case of monoclinic, there are also three lattice parameters because all are not equal. In case of triclinic, A is equals to B is not equal to C. So this is again there are three parameters, and again in case of trigonal, A is equals to B equals to C. So it has only one lattice parameter. So if you go to the question, the question was the space lattice with two lattice parameters belong to the crystal system. So out of which we need two lattice parameters. So two lattice parameters, which crystals has two lattice parameters? This is 2, 2. So for tetragonal, this is A equals to B not equal to C. This is two lattice parameter. Then for rhombohedral, A equals to B equals to C, that is trigonal, but alpha equals to beta equals to gamma not equal to 90 degree. But since here alpha, beta and gamma all are equal, we can take it another lattice parameter, that is A and alpha lattice parameter. So this is also in case of, so this is A, B and C 1, then alpha, beta, gamma, out of which there will be 1, so there will be 2. So in case of trigonal, tetragonal and hexagonal, we have two lattice parameters. So if we go to the question, so in case of tetragonal, A equals to B not equal to C, and alpha equals to beta equals to gamma equals to 90 degrees. So here are two lattice parameters A and C. Then in case of rhombohedral, A equals to B equals to C, alpha equals to beta equals to gamma not equal to 90 degree. So here this is one lattice parameter and here this is another lattice parameter. So A and alpha, these are two lattice parameters. And in case of hexagonal, A equals to B not equal to C. So here there are A and C, there are two lattice parameters. So the option A will be correct. However, in case of triclinic, monoclinic and cubic, they have different numbers of lattice parameters. And in case of tetragonal, rhombohedral and hexagonal, there are two lattice parameters. So the crystal system that belongs to two lattice parameters or that can be represented by means of two lattice parameters are tetragonal, rhombohedral and hexagonal. I hope this is clear to you. In going to question number 8, the effective number of lattice points in the rhombohedral unit cell is option A is 8, option B is 4, option C is 2, and option D is 1. So I'll give you a few minutes to try this question and then I will discuss. So in case of rhombohedral unit cell, at each corner point we have an atom. So if you see, if you talk in terms of two dimension, suppose I will draw a simple square lattice. We have atoms at each corner. So now this atom is again shared by another three lattice. Or in order to enclose this atom, we need four lattice. So this is one, this is two, this is three, this is four. So this particular atom is contributing to four lattice structures. So the contribution of each atom to each lattice is 4, 1 by 4. So since there are four atoms at four corners, so the total number of effective, so the effective number of atoms per each unit cell will be 4 into 1 by 4, that is 1. Similarly, if you talk about three dimension, then each corner or each atom at the corner will be shared by four structures. So if you stack, so this is 4, if you stack another 4 that is above that particular structure, then will be 8. So, so then there will be total 8 number of crystals to cover the atom. So the atom is contributing, equally contributing to 8 crystals or 8 unit cells. So the contribution of each atom to one unit cell is 1 by 8. So now if you talk about the three dimension, one atom here, one here, one here, here. There are 8 atoms and each atom contribute 1 by 8. It will be 8 into 1 by 8, which will be again 1. So the effective number of lattice point will be 1 in case of rhombohedral unit cell, because irrespective of whether it is rhombohedral, cubic or tetragonal, they are they have 8 corners and each lattice point corresponds to or contribute to 8 unit cells. So the effective contribution is 1 by 8, and since there are 8 number of atoms, 8 number of points, it will be 8 into 1 by 8, that is 1. So the effective number of lattice point will be 1 in case of rhomboidal unit cell. Then question number 9, the effective number of lattice point in the unit cell of an end-centered monoclinic lattice. So in case of end-centered monoclinic lattice, it will be different because it is end-centered. So there are extra points that are present at the ends. So the options, so the options are option A1, option B2, option C4, and option D5. So I will give you a few minutes to try this question or think about this question, and then I will discuss. In the meantime, for your reference, I am opening this slide. So from this slide, you can see in case of side centered or end centered, this is C. So in case of side centered, if you see this structure, at the ends, there are extra atoms present. So how these will affect the effective number of atoms per unit cell, you need to think about it. So if we see, in case of an end-centered monoclinic lattice, so suppose this is a structure. End center means there will be extra two atoms at the end faces, like one will be here in this face, and in this face one will be present at the center. So like in the previous question, since there are 8 atoms and each atom contribute to 8 crystals, so contribution from 8 atoms will be 1/8, so total will be 1. And again, if you see, if you draw another crystal structure here, so it will again, so this, the atom that is present at the face, it will contribute to 2 crystals. So because if you draw another crystal here, it will be enclosed. So this atom contributes to 2 crystals. So same type of atoms present are two. There are two atoms that are of same types that will contribute half. So it will be 2 into 1/2. So again 1. Total will be 2. So the effective number of lattice points in the unit cell of end center monoclinic lattice will be 2. Similarly, if you talk about body center cubic, so in case of body center cubic, in addition to the atoms present at the corner, one atom is at the center. So since this atom is inside the crystal or inside the unit cell, so the whole it wholly contributes to the crystal structure. So it will be, so this from this corners it will be 8 into 1/8 plus 1, because it contributes wholly. So it will be 1 plus 1 2 again. So for body center cubic, effect number is 2. For simple cubic, effective is 1. For end center cubic, effective is 2. And for face center cubic, if we talk, so in case of face center cubic, in at all faces, there are atoms present. So there are 6 faces. So there will be 6 atoms that contributes half. So it will be 3. So 3 plus this one, it will be 4. So in case of face center cubic, the effective number of lattice point in a unit cell is 4. So the correct option will be, if for this particular question, in case of end centered molecular lattice, the option B will be correct. That is, the effective number lattice point is 2. I hope this is clear to all of you. Then question number 10. The number of unit cells in 1 meter cube of FCC of nickel, where the radius of nickel atom is 1.243 angstrom. The options are option A 2.3 into 10 to the power 28, option B 4.2 into 10 to the power 28, option C 6.5 into 10 to the power 28, or option D 18.4 into 10 to the power 28. So as I discussed, so if you talk about the face center cubic, so suppose this is one face. So suppose this is one face. So if you, let me draw it proper cube. So one atom is present at the, then one is here and one is here. So technically all these shapes will be same, should be same, because, so let me do this, otherwise it will be confused. So let me draw 3 same. So one will be like this, another will be like this, another will be like this. So this is the actual face of a face center cubic crystal. So here if you see, if this is R, then total this is this is R, this is R, and this is again R, and this is R. So this is 4R. So in case of face center cubic, and if this is A and this is A, so this diagonal is root 2A. So as it has been already discussed in the class, 4R is equals to root 2A. So the relationship between A and R is A is 2 root 2 R. So the volume of, if A is the side, then volume will be A cube. So AQ is the volume of one unit cell, and we, the number of unit cells in 1 meter cube of FCC crystal. So A is equal to 2 root 2 R. Now the volume of one unit cell is AQ. So volume will be AQ, that is 2 root 2 R cube. So it will be 2 root 2 into R is given 1.243 angstrom. So 1.243 into 10 to the power minus 10 cube meter cube. So which will be, so the volume will be 4.345 into 10 to the power minus 29 meter cube. And we know, so the number of unit cells in 1 meter cube will be number of unit cells in 1 meter cube will be, so this is the volume of one unit cell. So the number of unit cell in 1 meter cube will be 1 by 4.345 into 10 to the power minus 29, which will give 2.3 into 10 to the power 28 number. So the number of unit cell in 1 meter cube is 2.3 into 10 to the power 28. So option A will be the correct option. Now again consider, again going to the next question, question 11. The number of members in the family of the planes 1, 2, 3 in cubic crystal are option A 8, option B 12, option C 24, and option D 48. So if you talk about the family 1, 2, 3, then it can be 1 or minus 1, 2 or minus 2, 3 or minus 3. So if you see 1, 2, 3, it can be arranged in 6 ways, that is 3 factorial ways. It will be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So this is the 6 ways. So similarly, now this is 1, then 1 minus 1, 2 minus 2, 3 minus 3. So for each position, we have two possibilities. So the total number of combinations will be 2 into 2 into 2, 8 combinations. If you consider minus 1, 1, 2 minus 2, 3 minus 3. So corresponding to each 8 contributions, again we have 6 ways. So 8 ways we can write minus 1, 1, 2 minus 2, 3 minus 3. And for each 8 way, we have 6 ways to write 1, 2, 3 in different order. So there will be 8 into 6, 48 ways. So the total number of members in the family 1, 2, 3 is 48. So for example, suppose this is one, so this one from this, for this 1, 2, 3, there are 6 ways. So one is minus 1, 2, 3, another is 1, 2, 3, another is minus 1, minus 1, minus 2, minus 3, then minus 1, 2, minus 3, 1, minus 2, 3, 1, 2, minus 3. So there are 6, sorry, not 6, there will be another. So another will be minus 1, minus 2, minus 3 present. 1, 2, 3, 1. Another will be 1, minus 2, minus 3. It will be minus 1, minus 2, 3. So these are 6 plus 2, 8 ways we can write. And for each 8, there are 6 combinations. So it will be total 48 combinations. Then write all the directions, that is the number of members in the family 110. So since it is 110, so 110 can be arranged in 3 ways. That is, so 110, there will be again 1 minus 1. There will be 4 into 3. So there will be 12 ways. So how the 12 ways will be? What are the 12 ways? So what we can do, suppose, so this is the family 110. So now this 110 we can write as 110 minus 110 1 minus 10 minus 1 minus 10. So there are 4 ways. So now again this 110 can be written 101 110 011. So this is 3. Again, this will be 3. This will be 3. This will be 3. So there are 4 into 3. That is 12 number of members in 110 family. So the correct option will be option C. That is 12. Then the last question of today's session. The minus 1, 1, 1 plane is parallel to, options are option A 1, 1, 1, option B minus 1, 1, minus 1, option C 1, minus 1, minus 1, and option D 1, 1, minus 1. So this is a really interesting question. So I will give a few minutes to think about this question and then I will discuss. So if you see, so we have a formula for two planes to be, so if there are two sets of HKL values, the angle between the two planes or the direction cosines can be given by cos theta is equals to h1 h2 plus k1 k2 plus l1 l2 divided by h1 square plus k1 square plus l1 square root into h2 square plus k2 square plus l2 square root. So for the plane -1 plane is to be parallel, we need theta to be 0 or 180 degree. So if you see, since it is 1 for each component, whether it is -1 or 1, square will be 1 only. So the denominator will be root 3 into root 3. It will be 3. So in the numerator, so for cos 0 is 1 or cos 180 it is -1. So we need either 3 or -3. So if you see the combinations, this is -1, 1, 1. So if we multiply it 1, 1, 1, it will be -1, 1, 1. So it will be 2. So if you multiply -1, 1, 1, it will give you 2. So it is not correct. If you multiply this -1, -1, so this is, so it is -1, 1, 1. This will be -1, -1, 1. 1, 1 is 1, -1, -1, -1, -1, -1, 1. So it will be -1. So again, it is not correct. So again, this is 1, -1, -1. So -1, 1, 1. If you multiply, -1 into 1 is -1. 1 into -1, -1. So this will be -1, -1, -1. That is -3. And again, for this, again, it will be not equal to 3 or -3. Again, this option is not correct. So if you see, suppose HKL, H1, K1, L1 is -1, 1, 1, S2, K2, L2 is 1, -1, -1. Then cos theta will be -1 into 1 plus 1 into -1 plus 1 into -1 divided by 1 square plus 1 square plus 1 square into 1 square plus 1 square plus 1 square. It will be -3 by 3. It will be -1. So theta will be 180 degree. So the correct option will be option C. So the -1, 1, 1 plane is parallel to 1, -1, -1. So simply you just need to reverse the sign. So this is -1. This will be, you multiply minus here. It will be 1, -1, -1. So the option will be option C. I hope this is clear to everyone. So with this, I come to end of this today's interaction session. So in the next interaction session, I'll be solving a few more problems, which will be based on the week 3 of the lectures. So as the course goes on, I'll be happy if some more students join. So for today, that's it from my side.